Hello everyone, this is Sir Aris. Today we will talk about linear algebra. We'll start with matrices and also talk about row reduction. Matrix is simply, in the plural form is matrices, is simply a rectangular array of quantities. For example, you have matrix A equal to this array of 1 5 minus 2, and in this lower row you have minus 3 0 and 6. We indicate a matrix by Roman letter such as this here A. The letter doesn't have a numerical value, it simply stands for the array. To indicate a number in the array, we will write a subscript ij, where I is the row number and j is the column number. So here in this case, you have two rows. You have row 1 and row 2, and three columns, column 1, 2, and 3. So if you want to write A in terms of indices, you have A equals um, A 1, 1 for row 1, column 1, A 1, 2, row 1, column 2, A 1, 3, row 1, column 3, A2 1, row 2, column 1, A2 2, row 2, column 2, and A2 3. So that comparing with this matrix, you have A1 1 equals 1, A1 2 equals 5, A1 3 equals minus 2, A2 1 equals minus 3, A2 2 is 0, and A2 3 is 6. We will call a matrix with m rows and n columns as uh, an m by n matrix, or you can write a times symbol m by n matrix. So for this matrix A, it has two rows and three columns, so it is a 2 by 3 matrix. Another definition, you have a transpose of a matrix. It's written as, so the rows, we write the rows as columns, or we interchange rows and columns. So if you have our matrix here, 1 5 minus 2, or 1 5 minus 2 becomes the column 1 5 minus 2. The row minus 306 becomes this column minus 306. AT, so A superscript T, is the transpose of the matrix. Using index notation, the um, the elements of AT, ij, is just equal to the element of A, matrix elements of A, ji. Here we'll develop methods of working with sets of linear equations. If you have a set of equations here, 2x minus z equals 2, 6x plus 5y plus 3 is equals 7, 2x minus y equals 4. We wrote this in standard form, that is x, y, and z, each terms line up. So here all x's are lined up, y's lined up, z's lined up. The constants on the right are on the right hand sides of the equation here. Several matrices of interest are connected with this set of equations. First is the matrix of the coefficient, let's call it M. So here, the coefficients here can be written in matrix form. You have 2, 6, 2 in the first column, 0, 5, minus 1 in the second column, and minus 1, 3, 0 in the third column. We also have two 3 by 1 matrices. Let's call it R. You have X, Y, Z. Here you have X that corresponds to this X, Y, Z here. And K, 2, 7, 4 are the constants on the right hand side. If you use indices, take note that Rm is M11, M12, M13, M21, M22, M23, M31, M32, and M33. R for XYZ. If we want to write this in terms of indices, let's write it as x1, or let's say in this case, let's write it as R1, R2, and R3. And finally for K, let's call it K1, K2, and K3. So our set of linear equations can be written as M11 R1 plus M12 R2 plus M13 R3 equals K1, M21 R1 plus M22 R2 plus M23 R3 equals K2, and M31 R1 plus M32 R2 plus M33 R3 equals K3. So that would look similar to this. So you have this K1, K2, K3, R1, R2, R3, and these are the coefficients, which are these elements M11 and so on. This we can write as a product of this. So M times R equal to K, or in summation form, we can write for I equals 1, 2, or 3, you have summation of J from 1 to 3 of Mij times Rj equals Ki. Now let's check. If I is 1, for example, then you have sum j of j here from 1 to 3 equals Ki is 1. So this is 1. The first index is 1. So you have 1 here, M1. The second index would run from 1 to 3. So you have here 1, 2, 3. The j also here on R runs from 1 to 3. 1, 2, and 3. You do the same thing for I equals 2 and 3. You get these equations. So basically we can write our set of equations in terms of this matrices M times R equals K, or the matrix of coefficient M times R, which is the matrix corresponding to this, or here you have X, Y, Z, and K, the constants. We can display all essential numbers in a set of equations as a matrix known as the augmented matrix. The first three columns of A are just the coefficient matrix M, and then we add in the fourth column the constants. So for example, for the set of linear equations here, we have the M uh, matrix, and then we add on one column this 2, 7, and 4. So we have this. We'll use a process called row reduction to solve the set of linear equations. So let's write again A as 2, 0, minus 1, 2, 6, 5, 3, 7, 2 minus 1, 0, 4. This corresponds to the set of linear equations 2x minus 1 equals to 6x plus 5y plus 3 z. There's a z here. Actually, let me replace this with z. So 3z equals 7. 2x minus y equals 4. To solve this equation, so we want to find values of x, y, and z, we just reduce this augmented matrix. First thing we can do is multiply first row by 3 and subtract from second row. The result for that, we replace to either row 3 or row 2. So the two rows involved, we can replace them with the resulting uh, row. So here, let's say this is not going to be A, this is the reduced version of A. Um, we say we want to remove um, the second row, okay, or we replace it with the result of this operation. So we keep 2, 0, minus 1, and 2. Multiply first row by 3. So we multiply this becomes 6. And then subtract from second row. 6 minus 6, that's 0. 5 minus 0, that's 5. 3 minus a negative 3. So multiply this by 3, it's negative 3. 3 minus negative 3, that's 6. 7 minus 2 times 3 is 6, so that's 1. 2 minus 1, 0, and 4. Okay, this is a reduced version, but this is not the completely reduced form that we want. We continue. We instead of multiplying, we subtract first row from third row, and let's choose to remove this, replace this with what we get from this operation. So we keep 2, 0, minus 1, and 2. 0, 5, 6, 1. Subtract first row from third row, so 2 minus 2, that's 0. Minus 1 minus 0, that's minus 1. 0 minus negative 1, that's 1. And 4 minus 2, that would be 2. Okay, so we keep this in mind. What we can do next is multiply third row by 5 and then add with second row. And then suppose we want to replace the third row. Okay, multiply third row by 5 and add to second row. Okay, multiply this by 5. So we keep the first row 2, 0, minus 1, and 2. We keep the second row 0, 5, 6, 1. We replace the third row with whatever the result here is. So multiply third row by 5, multiply this by 5, add that to second row 5, minus 5 plus 5, that's 0. Um, here, 5 plus 6, that's 11. 5 times 2 is 10 plus 1, that's also 11. Next, multiply first row by 11 and add to third row. We want to keep third row. We can replace this first row. Multiply that by 11. 2 times 11, you have 22. 0 is, so that's 0. 0 plus 0, so 22 plus 0 is 22. Minus 11, minus 1 times 11, that's minus 11. Plus 11, that's 0. And here, 2 times 11, that's 22. Plus 11, that's 33. And we keep the others, 0, 5, 6, 1, 0, 0, 11, 11. And then we can also multiply second row with 11 over 6, then subtract from third row. So we can keep this. We are only working on second and third row. We have 22, 0, 0, 33. We'll try to replace the second row. Um, multiply second row with 11 over 6. So 11 over 6 times 5. That's subtract from third row. 0 minus 5 times 11 over 6. So that's negative 55 over 6. Multiply 6 by 11 over 6 is 11. So 11 minus 11 is 0. And the last one here, 1 times 11 over 6 is 11 over 6. So 11 minus 11 over 6 would be, so 11 minus 11 over 6, that's 66 minus 11 over 6, or 55 over 6. So this is 55 over 6, and 0, 0, 11, 11. We can also divide each row by by a certain number. Let's say we'll divide first row by 22, um, second row by negative 55 over 6, and then third row by 11. So we get 22 divided by 22, that's 1. 0, 0, 33 divided by 22, that's 3 over 2. Negative 55 divided by negative 55 over 6, so that's 1. 0, this number divided by negative 55 over 6, that's negative 1. And finally, you have 0, 0, 11 divided by 11, that's 1. Here's also 1. And this corresponds now to a set of linear equations: x plus 0 y plus 0 z equals 3 over 2, y equals minus 1, and z equals 1. And we have finally solved the set of linear equations. Um, in a reduced row a matrix, the number of non-zero rows is called the rank of a matrix. So for example, here, this is the reduced form. The number of non-zero rows are 1, 2, and 3, so it has rank 3. Now you can see there's a general problem of solving m equations in n unknowns. The coefficient matrix of the coefficient matrix M has m rows corresponding to m equations and n columns corresponding to n unknowns. The augmented matrix A has one more column. And the following summary outlines three possible cases. If the rank of M is less than the rank of A, then the equations are inconsistent and there is no solution. If the rank M equals rank A and they are equal to the number of unknowns, then there is one solution. If rank M equals rank A uh, equal to R but less than N, N is the number of unknowns, then R unknowns can be found in terms of the remaining N minus R unknowns. For example, you have a set of equations here, and given, suppose if you want to verify, you can also get this. So given the row reduced matrix as this, we want to find the solution. So from the reduced matrix, the solution is you have here x minus 2z equals 3. So x can be written as 3 plus 2z. You have y plus z equals 4. You can write y equals 4 minus z. Um, for this example, you have m equations, so you have 4 equations, but there are 3 unknowns, so n equals 3. So if you want to solve the rank of m and rank of a, this is a, so this is, or a would be the augmented matrix. This is the row reduced form of the augmented matrix, and this has two non-zero rows. These rows are all zero, so the rank of A is equal to 2. For M, we need only this uh, or this part. Okay, we exclude this. For this case, there are still two zero rows and two non-zeros, so rank of M is 2. They are the same, so it's either this second case or this third case. There are 3 unknowns, so n equals 3, but rank of A and M are 2. So 2 is less than 3. Therefore, there are 2 unknowns that can be found in terms of the remaining n, or 3 minus 1, 3 minus 2 unknown. So the n is 3. The rank 2 is less than 3. So there are 2 unknowns, which are actually this x and y, which can be found in terms of the remaining 3 minus 2. 3 minus 2 equals 1 unknown. That 1 unknown is this z.